At the end of part one, we wanted to measure the relative efficiency of more combinations of gears, but our testbed did not generate enough load to differentiate between the more efficient drivetrains. For example, two 40-tooth gears versus three 24-tooth gears. As such, we intended to return to lifting weights. We had done this several times for motor testing, and we thought it was a reliable methodology. Unfortunately, it did not work well this time. We got very sporadic results even after doing multiple pulls, dropping the min and max values, and not recording runs where we may have operated the testbed improperly, stopping too late, etc. After seeing erratic data across many drivetrain types, from 16-tooth gears to even belts, we decided that we needed a more constant load.
So we were wondering why we got a bunch of fluctuations in the actual measured result in the speed computer. Well, in our teardown video, we opened this up, and this basically takes 3 samples per revolution. There's 3 clicks on the circuit inside here, so 1, 2, 3 every time it goes around. This drum's about 3 centimeters across, and this weight is going up at most 74 or so centimeters, which means the drum's got a diameter of 3 centimeters. That's about a circumference of 9-ish centimeters. So we're making only about 8 revolutions to raise the weight the full distance, which is 24 samples, and that's not very much resolution. And I'm not too surprised that the numbers shown on the speed computer fluctuate so much.
Since this methodology had worked before, we eventually suspected that a low battery in the speed computer may have affected its reliability, but not before we looked at alternative testbeds. We wanted something that could run continuously and reach a steady state, but also something that would maintain a consistent torque. In our last round of motor testing, we tried Technic clutch gears, only to discover that they increase in resistance as they warm up. Eventually, we settled on using banks of rubber tread. While the oval shape of individual tracks created varying friction, stacking several out of phase smoothed it out and increased overall load. Driving this mechanism with the motor lowered its output RPM from 420 to between 400 and 380, suggesting torque in the range of 1 Newton centimeter. For the sake of this test, we recorded numbers in the middle of a fluctuating result, in this case 390. So back to testing gears. With this new test bed, it took just 3 8-tooth gears on pins to stall the motor. 3 8-tooth gears on axles obviously did better, but they still sapped a noticeable amount of power, bringing the output RPM down to 350. Adding a 4th 8-tooth gear brought it down to 290, and we can see how power loss increases exponentially with more stages in both cases. Now, we covered the same distance with larger gears to see how they fared. Two 40-tooth gears and three 24-tooth gears on axles registered the same 370 RPM. Again, this means less that they perform the same and more that the limited resolution of the speed computer cannot detect the difference. Installing the middle 24-tooth gear on a pin reduced the measured RPM to 350. A similar story unfolds for four 16-tooth gears. We measured 350 RPM with the center two on axles and pins, but this setup also covers one more stud. Axles are probably on the high side and pins on the low side of the 340 to 360 RPM range. Looking at this a different way, three 8-tooth gears with the center one pinned already drops output RPM to 330 while only covering two studs. For the same power loss using 40-tooth gears, four of them on pins, we can cover 30 studs axle to axle. We can also cover the same 30 studs with bevel gears. This uses fewer gears but also smaller gears, and we have to support a long shaft, which has its own problems. Surprisingly, this setup offered little measurable difference in performance, running at 350 RPM. Initially, we used universal joints to avoid over-constraining a long axle and to reduce friction from bent axles. We repeated this test with regular joiners, and it also did not make an appreciable difference, though we could definitely see the rigid axle wobbling. So for the TLDR, I'd reiterate the lessons from the first one. Don't use small gears and don't use pins. Large gears on pins can outperform small gears on axles, but not vice versa. Chains or belts could be even more efficient, but they come with their own problems.
So what actually happens when we have two gears turning? Where are the forces? So a gear has these teeth, but there's an effective size of the gear called the pitch diameter. And that's the distance between, well, it's twice the distance between the center of the gear and the point where the gear teeth contact each other. So you can draw a gear. You can represent a gear by just a plain circle. Another plain circle like this. They're touching each other. And this is the pitch diameter. If you actually draw the teeth, it's going to be something like, the teeth are going to overlap the pitch diameter like this. But you can think about the gears like that. And the forces between these gears isn't exactly parallel here. They actually go at a slight angle like this. And this is called the pressure angle. And this is going to be something like 20 degrees. So let's ignore for a moment why you have this and where it comes from, and note that basically all gears have this. This means that any torque you send through this gear gets transmitted as a force at this angle. And so this has a couple of implications. The first is, think about a gear like that. This force has a tangential component here, which is basically going to be your useful torque. And then it's going to have a radial component here. And this is force that's going to push the gears apart from each other. And so, of course, by Newton's third law, your other gear here is also going to have a force doing that. And this is why if you actually just, put one gear on a beam and another gear on a beam and don't connect them and you turn this on, they'll fly apart. So let's say you have a pair of gears transmitting a constant torque. And you could choose a few different sizes for these gears. So let's take two extreme cases. We'll take a small pair of gears, and we'll take a big pair of gears. And these gears are going to transmit the same torque. And as we said earlier, the torque is transmitted by a force at this contact point here. Since the diameter of this gear is bigger than the small gear, the amount of force on right here can be lower because torque is force times this radius here. So you have a big radius and a small force equal the same torque. And over here, you have a small radius. So to get the same torque, you need a much bigger force to get the same torque. So what this means is the force on the gear teeth, and consequently the force on the gears, both this way and this way, both tangentially and radially, is going to be bigger for small gears than for big gears.